Welcome to the Prelude to Computer Science, Interlude number 5. Back in Interlude number 4, I had shown how to convert from base 10 to base 2 using a method that I call the method of successive remainders. And then a week or two ago, a user wrote a response to another one of my videos and asked the question, why does that they said that they had learned that method back in school and was asking why the method worked. At first I thought I could write I could write in a sentence or two why the method works, but that really wouldn't explain why. And then I thought I could do a proof, but then that doesn't explain it either. Unless the person's a mathematician. So I think what I'll do is I'll use a method that is commonly used by engineers, scientists, mathematicians when they're faced with a problem that they don't know the answer to, and they don't know what to do. What they'll do is instead of solving the problem that's being asked, they'll solve a problem that's easier than the one. They'll try to find the most trivial example of that problem that they can find and solve the trivial example, and then see if that gives them any insights into coming up with a more general solution. So I'm going to use an example here. Let's say we write down the number 217. 217. Now, if we divide this by 10, we're going to get 21, obviously. We're going to get 21, and the remainder is going to be 7. The remainder is 7. So if we take divide the 21 by 10, that's going to give us a remainder of 1, and it divides out to 2. So then we go around this, reading them off backwards, and we get 217. So indeed, 217 base 10 is equal to 217 base 10. So let's see if what we can figure out from this. What we did is we had the effect of this was to peel off the modulus operation, or the remainder operation, had the effect of peeling off the least significant digit as the remainder. And then the division had the effect of doing a right shift of the digits, where you just throw away the least significant digit and you just do a right shift, what we refer to as a right shift. So then we repeat the operation, and this time the 1 is the least significant digit, and indeed that is the remainder. We divide by 10, and we're left with a 2, and of course 10 doesn't go into 2 evenly. Or a whole number of times. So it stops at this point, and we read off backwards. So what's happening here when we do this conversion from base 10 to base 10 is we're peeling off the least significant byte at each step, and we're and the division itself consists of a right shift. So that can give us a little bit of a hint of why this might work on something else. But let's try another very simple example. Let's do a base 2. From base 10 to base 2, let's convert, say, the number 13 to base 2. Now, 13, now, it just so happens that I know that the the binary representation of this is 1101. So I'm going to write that out there. That's what the result has to be, 1101. And let's see if we can figure out if something going on here. Let's divide this by 2, and that's going to leave us a 6. It goes in 6 times and leaves a 1 remainder. We go in, and the 6 here is the binary representation for that is 110. I just happen to know that. So we divide 6 by 2, and that's going to give us 3 with a remainder of 0. Now, the binary of a 3 is 11. And divide that by 2, and that's going to give us a remainder of 1, and it goes 1 time, of course. And the binary of that is, of course, 1. We read it off in reverse, and indeed 1101 is the same thing as that. Once again, what we did is the 1 here is the least significant digit or bit in the correct string. So that 1 is that 1. And then we right shifted it, so this comes down to there. So we're getting rid of the least significant 1, and we're just right shifting. Then we the least significant bit here is a 0, which is there. And of course that gets right shifted. We lose the 0 and it just becomes a 1 1. And then the least significant bit there is a 1, which is here. And then that gets right shifted, and it's just a 1 left. And that's it. So here's the deal. The reason why it works, why the method works. Whatever number you have and whatever base you're converting to, there is a number in that base. And you're dividing by, since you're dividing by the base of the number, the remainder is going to be whatever is in the rightmost position, whatever is there. And then when you actually do the division, that's effectively a right shift in that base. So that is my explanation for why that method works. And you know, we could do a proof of it. I think I've given enough information that we could do a proof of this. But the goal here is not to do a proof, but just to make help you understand intuitively what's happening here. So thank you very much. Thanks for the question, and I hope that this explanation makes sense to you.